So today we are going to start with electrochemical series. This is in continuation with the classes already we have done. The very first class was which one? It was the electrochemical cell. We did the Daniel cell there, okay, zinc copper electrode, and then we saw how the cell reaction takes place, what is the cell representation, how to calculate the EMF there, what is the Nernst equation, and how thermodynamically we can see the Gibbs free energy is working on the Daniel or galvanic cell. So today, while talking about electrochemical series, the very first thing we have to know is uh, what is the single electrode potential? Okay, when any metal is dipped in the solution of this metal salt, at that time there can be two things which can happen. First is there can be a oxidation or there can be a reduction. There can be oxidation or there can be a reduction. We have a nanonym, no? What is oxidation? Oxidation is oil. Oxidation is loss of electron. And what is the reduction? Reduction is Rig. Reduction means gain of electron. Whenever a metal electrode is dipped in its salt solution, there can be a loss of electron or there can be a gain of electron. While doing so, there will be a tendency to lose or gain electron. This tendency to lose or gain electron when it is contact with its own ions in the solution is called the electrode potential. Okay, what is the electrode potential? The tendency of an electrode. This is one electrode. You can see the metal electrode. It is in contact with what? Its salt solution. So the tendency of the electrode to lose electron or gain electron is called electrode potential. If suppose it is losing the electron, losing the electron is what? Oxidation. Oxidation is oil. Oxidation is loss of electron. If it is losing the electron, then this is known as oxidation potential. Okay. In the similar manner, if the metal is gaining the electron, that is what is Rig? Reduction is gain of electron. So if the metal is gaining the electron, means it is undergoing reduction. So then that electrode potential is known as the reduction potential. So how many types of electrode potential we have? Oxidation potential and reduction potential. If it is undergoing oxidation, it is oxidation potential. If it is undergoing reduction, it is a reduction potential. So let's see the tendency of an electrode to lose or gain electrons when it is in contact with its own ions in the solution is called electrode potential. This is the definition of electrode potential. The tendency of an electrode to lose or gain electron when it is in contact with its own ions in the solution is called electrode potential. If it is losing the electron, means it is getting oxidized, then that electrode potential is called oxidation electrode potential. If it is gaining the electron, it is called reduction. Then such type of electrode potential is known as reduction potential. So you can have different metal and you can have different non-metal which is undergoing such type of processes. For example, here you can see a zinc ion that can be a zinc sulfate, it can be a zinc nitrate, it can be a zinc chloride. Any metal salt solution which is in contact with its electrode, that is zinc metal. This is in aqueous solution, children, and this is in solid. And the phase difference is shown by one single vertical line. Okay. Here you are having Cu2 positive, which can be a copper sulfate solution, which is in contact with copper electrode. In this, you can see Mg2 positive is there, magnesium ions are there, which is in contact with magnesium electrode. These are all what? Metal electrodes, metal half cell you can say. And non-metal half cells, here you can say H positive, that is hydrogen chloride, HCl. Vertical line is phase difference from the aqueous layer to the gaseous layer. H2, that is hydrogen gas sent at 1 atmospheric pressure. And both the reactions are taking place on what? On a metal, which is the platinum. Okay, so this is the representation of which electrode. Yesterday we had seen that hydrogen electrode. Okay, this is a representation of hydrogen electrode. In the similar manner, another gas electrode is which one? Chlorine electrode. Same thing, only the chlorine gas is sent in place of hydrogen gas. So platinum, which is having the absorption of the chlorine as a gas and the chlorine ion in aqueous solution. Similar manner, another gas electrode is which one? Oxygen electrode. Here we are having oxygen gas which is sent and the solution is having some alkali in it. It can be a sodium hydroxide, it can be a calcium hydroxide, magnesium hydroxide, or sometimes water is there with little amount of any of the alkali salts are there. Then such type of electrode is known as the oxygen electrode. Okay, another one example is the bromine electrode. Here also we have an inert metal, that is platinum, and on the platinum there is absorption taking place and you are having a bromine gas with contact with any bromide ion like HBr, hydrogen bromide, and so on. So let's see here. This is our complete cell. Okay, our complete cell is there. In this complete cell, we are having on the right hand side a copper electrode dipped in a copper sulfate solution. On the left hand side, we are having a hydrogen electrode. Hydrogen electrode is also known as what? Our standard or the reference electrode. Okay, standard hydrogen electrode or SHE, standard hydrogen electrode. This is also known as a reference electrode. In IUPAC system of nomenclature, children, they have taken the standard hydrogen electrode potential as 0.000 volts. So when the total electrode potential of hydrogen is 0.00 volts, in our voltmeter, whatever we get, in our voltmeter, whatever value we get, that will be of the copper electrode. Okay. So here, what is the standard electrode potential? We have to maintain few standard conditions. Okay. The conditions are the concentration should be a unit concentration. Okay. The potential exhibited by a single electrode at unit concentration. The temperature should be 25 degrees. 25 degrees, when we convert it into Kelvin, we will add with what? 273. So we will get what? 298 Kelvin. Okay. So a unit concentration of the metal ion or non-metal ion solution at 25 degrees Kelvin in contact with a single electrode is known as the standard single electrode potential. Okay. Now, after knowing the basics, now we know what is electrode potential, we know what is oxidation electrode potential, we know what is reduction electrode potential, and we know what is standard electrode potential. Okay. After knowing all these things, now let's come to the definition of the topic, which is today's topic, that is electrochemical series. Now, the scientists, what they had done, they had taken some 10 or 15 different types of electrodes and different electrodes in salt solutions of their respective electrodes, and then they connected it with standard hydrogen electrodes. Okay, and then they took the different values of their potentials. Okay, all these potentials, they mostly saw it as reduction potential. Again, understand what is reduction. Reduction is gain of electron. So in each and every case, there was a gain of electron which was taking place. Okay. If there is an oxidation taking place also, they used to change the sign and then they used to make it as a SRP. SRP means standard reduction potential. And then what they did, they arranged all these half cell electrodes in a decreasing order. Okay, in a decreasing order. Few of the books shows increasing order, few of the books show decreasing order. But in the starting, what they did is they arranged all this standard reduction electrode potential in decreasing order and made it into a series. And this series is known as electrochemical series. Okay. So what is the definition of electrochemical series? All the standard electrode potentials arranged in decreasing order is called the electrochemical series. Okay, this is a descending order of their SRP. SRP means standard reduction So let's see here. Here you can see lithium, potassium, calcium, sodium, magnesium, aluminium, and so on. And here you can see the reduction potential. It is starting from minus 3.04 and it is going up till 1.69. Okay. So what is happening? The reduction potential is changing. Then based on this reactivity series or electrochemical series, lot of applications are considered. The very first one, the top elements which are present, that is lithium, potassium, calcium, are very, very, very reactive compared to the down, platinum, gold. So the reactivity of the elements on top is more compared to the reactivity of the elements at the bottom. Okay, that is the very first difference. Second one, the top one are more electropositive compared to the bottom elements. Okay, the electropositive character of the elements on top will be greater compared to the elements which are at the bottom. So first, what did we understand from the electrochemical series? It is in the decreasing order. Decreasing order of what? Of the SRP. What is SRP? Standard reduction potential. The top one is what? Top one is more electropositive. The downward is what? Downward is less electropositive. The top one will be more reactive. The down one will be less reactive. Okay. So here, let's move further ahead and see how we can study the electrochemical series. So here also you can see the complete electrochemical series. On the left hand side, we are having all the half cells, okay, arranged. In the middle, the reaction. Remember, RIG is what? Reduction is gain of electron. In each line, here you see cerium 4 positive plus electron gives cerium 3 positive. Aurum 3 positive plus 3 electron gives aurum. Cl2 plus 2 electron gives 2 Cl negative. So each and every case, you are having what? Addition of electron. When addition of electron is taking place, at that time what is happening? Reduction is taking place. But observe here, the 18th number, we are having the hydrogen. This is our hydrogen electrode, that is standard hydrogen electrode. And here what is our value? 0.06. Okay, our value is 0.06. Okay, many a time here if you see, it will be in the means from positive, it is coming to negative. Okay, from positive it is coming to negative. Sometimes they will arrange the previous one. If you see here, it is negative, then 0 will come, and then the positive will come. In any case, if you arrange whether in increasing order or decreasing order, that doesn't make any difference. Only we can understand it better if it is arranged in this way. We can say that which one will react, which reaction is more feasible, and what is happening in the reaction, which is oxidation, which is the reduction, and which is forming anode, which is forming cathode. All those things we can observe. Okay, so don't get stressed out if in one textbook you are having the increasing order, in another textbook you are having the decreasing order. Okay, both are okay. It's just arranged in increasing or decreasing order of the standard reduction potential, and this arrangement is known as the electrochemical series. That you have to keep it in mind. So basically what we are doing here, metals are arranged according to the tendency of their atoms to release electron. More the tendency of their atom to release the electron, higher they are located higher in the series. So the elements which are located at the higher part of the electrochemical series are more electropositive and have a higher tendency to release electrons to form a positive ion. Example, magnesium is more electropositive than copper. Okay, let's see the electrochemical series and see where is magnesium. Our magnesium is here. It is having what reduction potential? Minus 2.36. Where is our copper? Copper is down. It is having 0.339 with a positive sign. Okay, so magnesium is more electropositive compared to that of copper. Okay, in this way you can see that the ones which are on top are more electropositive, and the ones which are at the bottom are less electropositive. So the potential difference between the two metals can be deducted, okay, can be also calculated. The further apart between the two metals in the electrochemical series, greater is the potential difference between them. And the greater the voltage is produced by the cell. Let me show the example. If we look here, if I have one electrode as potassium, the another one is copper, okay? Which is more electropositive? Potassium is more electropositive. Which is comparatively electronegative? Copper is electronegative. Electropositive means what? It will undergo a loss of electron. If it's undergoing a loss of electron, the potassium will become what? Oxidation electrode. And copper will become what? A reduction electrode. Oxidation is always carried out on the left-hand side. Reduction is always carried out on the right-hand side. So you have the value of potassium as minus 2.936, copper as 0.339. So what you can do is you can calculate the EMF of the cell. What is the EMF of the cell? E cathode minus E anode. Or then taking the values, you can actually calculate the EMF of the cell. I'll show you further. Let's see. So just to revise it, this is what reactivity series of the metal. The metal on top are more reactive than hydrogen. Okay, the one which are placed above the hydrogen are more reactive than hydrogen. The one which are placed below the hydrogen are less reactive than the hydrogen. These are the more reactive metals. These are the least reactive metals. Higher the position of the metal in the electrochemical series, more electropositive is the metal. The greater the tendency of the metal atom to donate the electron. More electropositive means what? It will lose the electron very easily. If it loses the electron very easily, it will undergo oxidation, and thus it will undergo oxidation, and then it will donate the electron. And where the electron will go? The electrons will go to the one which is lying below. Okay, the oxidation cells are in your Daniel cell, if you can remember, the oxidation half cell was your zinc. Okay, the zinc was acting as what? Anode. So now you understand that in the electrochemical series, the one which is lying above are undergoing oxidation and they form anode. Okay, they form what? They form anode. Let's see here. If I have a combination of sodium and zinc, okay, I have a combination of sodium and zinc. Then what I will, sodium will act as what? Sodium will act as a anode because it will undergo oxidation. And what will zinc act as? Zinc will act as a cathode because it is undergoing reduction. So understand, children, the one which is lying above will undergo oxidation. It will act as anode. The one which is lying below will act as cathode and it will undergo reduction. Okay. So now how many things we have learned about electrochemical series? We know that the top one are electropositive. The bottom one are mostly less electropositive compared to the top one. The top one are more reactive. The bottom one are less reactive. The top one are forming what? Anode. The bottom one are forming what? Cathode. The top one are undergoing oxidation. The bottom one are undergoing reduction. So many things we have learned. By knowing the values of the half electrode potential, you can calculate the EMF of the cell. What is the EMF of the cell? EMF of the cell is E cathode minus E anode. So suppose I have a combination of sodium and zinc. So I'll say E of zinc minus E of sodium. Because zinc is what? Cathode and sodium is what? Anode. Okay. Let's, I'm unmuting you. I'll ask you questions. You people tell me. Okay. Okay, now I'm giving you a combination of aluminium and tin. I'm giving you a combination of aluminium and tin. Tell me, tin will act as cathode or anode? half cells, one is aluminum and one is tin. Okay? Tin will act as cathode or anode?
Anode.
No. Aluminium. The top one is acting as anode. The bottom one is acting as cathode. Okay? So aluminium will act as what? Anode, because it is undergoing oxidation. Okay? Tin will act as what? Cathode, because it is undergoing reduction. Okay? So if I give you a combination of iron and lead, tell me which will undergo oxidation? Iron and lead. Which will undergo oxidation?
Iron.
Iron will undergo oxidation. And lead will undergo what? Lead will undergo what? Reduction. Okay?
Reduction.
Reduction. And here, if I calculate the EMF of the cell, then it will be E of what minus E of what? Who is the cathode here?
Cathode.
Minus E of anode.
Cathode minus anode.
Anode. Who is the E of cathode? Lead. Okay, so E of lead minus E of iron. Okay, very good. So now I am muting you again, and then I'll continue. Okay. So just to sum it up, we have seen that in our electrochemical series, when we go down the series, the top one are what? Reduction potential decreases. Then obviously what will happen? The oxidation potential will increase. Non-metallic property decreases as we go from top to bottom. The metallic property increases. Strength of reducing agent increases. The strength of oxidizing agent decreases. The reactivity of non-metal decreases. The reactivity of metal increases. So the electronegativity of non-metal decreases. Electronegativity of metal decreases. Okay. Electropositivity of non-metal increases and electropositivity of metals also increases. So the thermal stability of metal oxide increases. So as we go down the series, we see all these different type of things which will take place. What is the use of electrochemical series? Electrochemical series actually allows us to predict the result in the displacement reaction, whether we can construct any cell and whether the cell will work properly. In that cell, which is the anode, which is the cathode, what is the total EMF of the cell? So all these things, without even connecting the circuit, we can actually calculate and we can tell all these things using the electrochemical series. So children, this is actually on paper. Okay, before doing practically, on the paper, you can do each and everything properly. And when you do it practically, you will see that the values will come absolutely right. So that is the use of electrochemical series. To see whether any reaction is feasible, it is spontaneous or not, we have to use this electrochemical series. Let's take one example. Now I have a magnesium metal which is dipped in a solution of copper sulfate. Okay. What will happen after some time? I'll see that the sparkling magnesium metal is having a coating of copper on top. So what reaction has taken place? The magnesium has reacted with Cu2 positive. From where did I get Cu2 positive? I got it from copper sulfate. And what has happened? The magnesium has gone inside the solution as Mg2 positive, forming magnesium sulfate, and this copper 2 positive has got absorbed on the magnesium plate, and it has formed a copper coating. Okay, this reaction has taken place. So, how can I use electrochemical series and tell you? I can say that the magnesium is above. Let me go back to my electrochemical series. Yeah. If you see, magnesium is on top, copper is at the bottom. Okay, so magnesium is more reactive, copper is less reactive. That's the reason what is happening. Magnesium is going inside the solution and it is allowing the copper to come and get absorbed on the surface. So the more reactive metal will displace the less reactive metal. More reactive metal will displace the less reactive metal. That has happened here. In the similar manner, if I react iron and Cu2 positive. That is displacement of copper metal from the solution of the copper salt using iron. This actually they will do it. They will take scrap of iron. Scrap of iron means pieces of iron, and they will put it in any of the copper salt solution, and they will extract copper metal out of it. This is done by people who want to take the copper metal out of the wires or any of this electrical things. No, copper is very, very expensive. So by using this scrap iron, you can actually extract pure 100% pure copper out of the copper sulfate solution. And here also see, unknowingly, without knowing the chemistry, those people are doing practically where we see, those people who work with the garbages and all, they will collect all these copper wires, and then copper wires or circuits, and they will dissolve it in one salt, and then they will use scrap of iron to get back the pure copper, and then they will resell it, and they'll get a very, very high price for it. Okay, that is one of the applications. Next one, here also you can see magnesium is higher in the electrochemical series than copper. Magnesium gives electrons to copper ion, and copper ion gaining these electrons from the copper atom will get absorbed, and they will form a brown solid. So the magnesium atom uses electrons to form a colorless ion which dissolves in the solution. So copper sulfate solution will lose complete copper and get absorbed on the metal electrode, and the magnesium will completely get corroded, and it will form a magnesium sulfate solution. Okay. Now, another application of electrochemical series is, again, summing it up, higher the reduction potential, greater is the tendency of the element to get reduced. Again, our non-M with the reduction is gain of electron. Lower the reduction potential, greater is the reducing ability. A metal placed higher in the series is anodic, means it forms the anode. Then the metal which is lying at the bottom, it will form a cathode. Knowledge of the electrochemical series helps in the selection of electrode assemblies to construct the galvanic cell of the desired EMF. So how much electromotive force I want? I can prepare the different types of galvanic cell by taking different half cells. The polarity of the electrode system and the electrode reaction can be easily predicted. Spontaneity and feasibility of the cell under the construction can be easily predicted. So, and we can calculate the EMF of the cell. Just now we calculated E naught of the cell is what? E right minus E left, or E cathode minus E anode. Okay, by knowing the different types of galvanic or the Daniell cell, and by knowing the values, you can calculate the EMF of all the different cells. Now, oxidizing and reducing ability. Okay, so relative ease of oxidation and reduction can also be predicted. So here in electrochemical series, how many things we can know is that an electrode with a high reduction potential will have a greater tendency to undergo reduction. So let's take one example. For example, I have a platinum metal which is in contact with fluorine gas and fluoride ions. So what is happening here? The fluorine F2 is getting reduced to F negative, okay, because its SRP is what? So I'll just revise what we had done in the morning. So in the morning we had started with electrochemical series. I'll just revise it and then I'll go further ahead. So we had seen what is the single electrode cell. The single electrode cell is when an electrode is dipped in its salt solution. Okay, at that time this electrode can either lose the electron or it can gain the electron. If it is losing the electron, it is known as oxidation, and if it is gaining the electron, it is known as reduction. So the potential which develops between the electrode and its salt solution is known as the electrode potential. If it is undergoing oxidation, it is known as oxidation electrode potential. If it is undergoing reduction, it is known as the reduction electrode potential. So further, we saw the definition. The tendency of an electron to lose or gain electron when it is in contact with its own ion in the solution is known as the electrode potential. This is the definition of electrode potential. That is the tendency of an electrode to lose or gain electron when it is in contact with its own ion in the solution is called electrode potential. If it's undergoing oxidation, it is oxidation potential. If it is undergoing reduction, it is a reduction electrode potential. Okay. Then we saw that how we can calculate the electrode potential. We have to connect the electrode potential, the different half cells. So we have to connect the half cell. For example, in this figure, you can see that the copper electrode is dipped in copper sulfate solution, which is connected to a standard hydrogen electrode. Standard hydrogen electrode is known as what? She. And its electrode potential is 0.00 volts. Yesterday, we saw the construction and the voltage of the standard hydrogen electrode. Okay. So since one is 0.00 volts, we know that the total EMF of the cell is equal to what? E cathode minus E anode. That is E right minus E left. That's the formula of the EMF of the cell. So if one of them is 0.00, whatever is the other person's potential, that will be for that half cell. Taking such type of Daniel cells, they have constructed almost some 30 or 40 different types of half cell and connected with She, and they have calculated the electrode potential of each and every half cell. And then what they have done is they have listed it down. Okay, they have listed it down, and this list of the different elements, whether it is metal or non-metal, with respect to its respective salt solution and its reduction potential, are arranged in a decreasing order. And this decreasing order value of the SRPs are known as electrochemical series. Sometimes it will be in a increasing order and sometimes it will be in the decreasing order. Both are okay. The reactivity series or electrochemical series is a set of metal or non-metal with respect to their respective salt solution, either in the decreasing order or the increasing order of their reactivity series. In all these electrochemical series, the middle one will be hydrogen, which will be 0.00 volts. Below hydrogen will be mostly positive. Above hydrogen will be mostly negative. And all are what? SRP. SRP means standard reduction potential are there. The top ones are more reactive. The bottom ones are less reactive. The top ones are known as electropositive. The bottom ones are known as electronegative. The top one can prepare anode. The bottom one can become a very good cathode. By knowing all these things, we can actually make different sets of Daniel cells, and we can calculate their EMF very easily. So here there is another one set in which they have arranged the standard reduction potential from positive, and here you can see hydrogen, which is 0.00, and then comes the negative. Positive, 0.00, and the negative. So all these things are arranged. So here this is also your reactivity series or your electrochemical series. So on the left hand side you can see these are the representation of half cells. In the middle you can see that it is undergoing reduction. What is a reduction? Reduction is gain of electron, and since it is gaining the electron, it is forming its respective either atoms or its respective ions. Okay, and what the third column will talk about what? The SRP. SRP is standard reduction potential. Okay, so this whole setup is known as your electrochemical series. So here we saw how the metals are arranged. Metals are arranged according to the tendency of their atoms to release electron. What is this? Reduction. Reduction is what? RIC. Okay. more the tendency of their atoms to release the electron, higher they are located in the series. So the top electrochemical series will have a greater tendency to release the electron. Elements located at the higher part of the electrochemical series are more electropositive and have a higher tendency to release the electron to form a positive ion. For example, we saw that magnesium. Here you see, where is magnesium? Let's see, uh, cannot see here. Here it is. So magnesium, this is on top. Copper, this is at the bottom. So magnesium is more electropositive. Copper is less electropositive. Magnesium will be more reactive. Copper will be less reactive. Okay. So magnesium will undergo which type of reaction? It will undergo a oxidation reaction, and copper will undergo which type of reaction? It will undergo a reduction reaction. So oxidation reaction means what it will form? Oxidation reaction means it will form a anode, and reduction reaction means it will form a cathode. Okay. So these were the things we saw in the morning. Yeah. Okay. So we had summed it up. Here we saw that the higher the reduction potential, greater is the tendency of the element to get reduced. Lower the reduction potential, greater is its reducing ability. This is the first application. We can easily find out from the electrochemical series which is undergoing, which is having a higher reduction potential and which is having a lower reduction potential. The second application of electrochemical series is a metal placed higher in the series will be anodic. Anodic means what? It will work as a anode, and the other metal which is lying below will work as a cathode. The third one is knowledge of the electrochemical series helps in the selection of electrode assemblies to construct galvanic cell of the desired EMF. Suppose, let's take one example. Okay, let's take one example. Now, I want to construct a, I want to have a galvanic cell which should have 1.11 volt of electricity, or EMF should be 1.11 volt. So what should I do? At that time, I can do one thing is, I can take zinc. Okay, where is my zinc? Okay, lithium, potassium, here, lead, yeah, zinc. I can take one electrode as zinc, which is having 0.762 volts, and another one I can take is as copper, which is 0.339. Okay, first I am taking uh, one electrode which is zinc, another one electrode which is copper. Okay, since I'm taking zinc and copper, so what is the EMF of the cell? Okay, if I have to write the EMF of the cell, EMF is equal to E of cathode minus E of anode. What is my cathode here? Copper is my cathode. What is the copper's value? 0.339. Okay, so 0.339. So here, what is the value of zinc? Minus 0.762. So minus of, in the bracket, minus 0.762. Okay, 0.762. Then I open the bracket, minus minus will become what? Positive. So 0.339 plus 0.762, that is equal to 1.1 volt. Okay, in this way, if I want an EMF of 1.1 volt, I can easily construct the galvanic cell with different electrodes. So this is a very important application of electrochemical theory, that without doing the practicals, on the paper only, you can do your homework and you can find out which electrode is best for your galvanic cell. Okay. Yeah. So here the first application, what I wrote just now, that is E naught of the cell is equal to E naught of right hand side minus E naught of left hand side. Okay. What is E naught of right hand side? Means in your galvanic cell, which is towards the right hand side. Right hand side is always cathode and the left hand side is always anode. Okay, so that will be E naught of cathode minus E naught of anode. Okay, so here cathode was what? Cathode was your copper and zinc was your anode. Okay, so copper's value was what? 0.34 minus of 0.76. So that came out to be 1.1 volt. Like this, you can calculate the EMF of the cell. So this is our first application. Okay. Another application is finding out the oxidizing and reducing ability. Which of the electrodes will undergo oxidation? Which of the electrodes will undergo reduction? That can be easily predicted by the electrochemical field. So relative ease of oxidation or reduction can be predicted. An electrode with a high reduction potential has a great tendency to undergo reduction. Again, what is reduction, children? Reduction is gain of electrons. Let's take one example. The SRP, standard reduction potential of the platinum, fluorine by F negative. Means this F negative is in which state? Aqueous state. This F2 is in which state? This is the gas. And this setup is which type of electrode? Gas electrode. And what is the standard reduction potential here? Plus 2.87. Okay. The system is having a very high standard reduction potential. Hence, we can say that the fluorine is easily reduced to fluoride ion. Because the SRP is more, the fluorine gets easily reduced to fluoride ion. On the other hand, let's take the SRP, that is standard reduction potential of Li positive oblique Li. Again, Li positive is what? Lithium ion in the aqueous solution, and Li is what? Your metal. 1 bar means what? There is a phase difference from liquid to solid. What is the SRP, standard reduction potential here? It is minus 3.05 volts. Compared to this, you can see the value is very less. Here it was positive and here it is what? Negative. Since it is having a very less value, hence we can say that the lithium is very easily oxidized to Li positive. Okay, and the reverse. Reverse means Li positive getting reduced to lithium will become very difficult. So such type of oxidizing and reducing abilities can also be studied with the help of electrochemical field. The third one is feasibility of a reaction. What do you understand, children, by feasibility of a reaction? How easily a reaction proceeds, whether the reaction is spontaneous or not, that is known as the feasibility of the reaction. Any Daniel or galvanic cell whose EMF is positive, then that cell is said to be a feasible cell. Means that reaction will take place easily. It doesn't require any external sources. Okay, it will be a spontaneous reaction only when the EMF is positive. If the EMF of the cell becomes negative, the cell is not feasible or it is not spontaneous. Now, in the physical term, we can say that the water falls from a higher level to a lower level. This is a feasible reaction or this is a spontaneous reaction. But if I have to take the water from ground floor to the 13th floor, what I required? I required one set of pump, I required one set of instrument which should take the water from the ground floor to the 13th floor. So that's known as a non-feasible reaction or non-spontaneous reaction. In the similar manner, remember, any cell which is having a positive EMF is a feasible cell. Okay, and if the EMF is negative, it's a non-feasible cell. The reaction won't take place spontaneously. You require an external to do the reaction. Okay, so the metal with lower SRP, SRP again is what? Standard reduction potential, can displace another metal with a higher SRP value. So always remember in your electrochemical series, the top one was what? Negative. The bottom one was positive. So the top one can always displace the one which is at the lower level. Let's take one example here. Zinc, which is a solid, is dipped in a copper sulfate solution. Now I'm not having zinc in zinc sulfate, I'm having zinc in copper sulfate solution. So zinc is lying above, copper sulfate, copper is lying below. Zinc means cell potential is around minus 0.76. Okay, the value is around minus 0.76, and here the copper is around 0.34. So what will happen? This is having a lower SRP. This is having a greater SRP. So that's the reason the zinc will react with the copper sulfate, giving out Zn2 positive, and copper will be absorbed on the electrode. So here what is happening? The 0.34 is of copper, minus 0.76 is of zinc. It is a lower SRP. This is a higher SRP. So that's the reason what will happen. There will be a feasibility of the reaction, or the reaction will be very, very spontaneous. Again, let's understand the word feasible and spontaneous means which takes place all by itself without any external aid. Such type of cell reaction are known as feasible or spontaneous cell reaction. Okay. Next application is replacement tendency. Which metal can replace which metal? That we have to understand. Higher positive value of SRP potential indicates greater tendency of the metals to assume reduced form, while higher negative value of SRP indicates greater tendency of the metal to assume oxidized form. Standard reduction potential values of copper and zinc we saw. In that we have a 0.34 volt of copper and minus 0.763 volt of zinc. Okay. So here the zinc has a much greater tendency to acquire Zn2 positive and compared to copper. So zinc will replace the copper from the solution. Okay. Again, let's understand here. Here you see in the previous slide I told you that what is the value of zinc? The value of zinc is minus 0.76. Minus 0.76 means it is having a lower SRP value. Since it is having a lower standard reduction potential value, at that time what will happen? The zinc will break down into Zn2 positive easily. Okay. Whereas copper 2 ion getting converted into copper, the value is how much? Plus 0.34. So that value is lesser. This is the main important thing, because of which what will happen is the zinc can replace the copper in the solution. Okay, because its SRP is very less, it can easily lose electron, and it can come here in place of the copper and form a zinc sulfate solution. And the copper, obviously, this person has come and it has taken its place. So that's the reason what will happen. The copper, he has to leave and he has to come out. Okay. So this is another replacement tendency. So you should remember in an electrochemical series, all those which are having negative SRP value are more reactive. They are having greater tendency to displace the metals which are lying below. Okay. Next one, displacement of hydrogen from dilute acid solution by the metal. Now we know that the hydrogen is having 0.00 volt. It is in the center. Some metals are lying above, some metals are lying below. Shall we see in our electrochemical series again? Let's go back and let's check out. Yeah, here you see. Here all are negative. Okay. So above copper, actually, here comes the hydrogen. Above the copper, we get the hydrogen. Here is my electrochemical series. Yep, here you see. 18th serial number, H positive, oblique H2, oblique PT. Okay, here what is 0.00? Definition is this is a standard reduction potential of She standard hydrogen electrode. It is also known as what, children? It is also known as the reference electrode. With respect to this She, that is standard hydrogen electrode, we have found out the electrode potential of all these elements. So the one which is lying above, okay, these are positive, these are negative. Actually, mostly the one which is having the negative SRP can displace the one which is having a positive SRP. So displacement of hydrogen from dilute acid solution by metal means any metal which is having the SRP value negative in the electrochemical series, means all these metals which are having the SRP value negative in the electrochemical series, they can reduce the hydrogen ion, H positive ion to H2 and displace hydrogen from the acid solution. So if I take hydrochloric acid, it's HCl, it is having H positive, nitric acid, HNO3, it's having H positive, sulfuric acid, H2SO4, it's having 2H positive. So all these H ions can be displaced and hydrogen gas will be liberated out. Only by whom? All the metals which are having a negative SRP value. Okay, the metals which are having a positive SRP value cannot do such. So this displacement can only take place by this. You can see here we have lead, tin, nickel, cobalt, cadmium, iron, chromium, zinc, aluminium, magnesium, sodium, calcium, potassium and lithium. Only these are the reactive metals which can displace H positive from the acids, not gold and silver. That's the reason your mother is wearing gold ornament and she's working with acids, that is citric acid or tartaric acid in the kitchen, and nothing is happening to her gold ornament. Why? Because these are having a positive SRP value. So whether she is using a tamarind juice, which is or a tomato juice or a lemon juice, all of them are having acids in them. Citric acid is there, malic acid is there, tartaric acid is there, and her hand is having bangles and rings. But nothing is happening to the gold. Why? Because these are having a positive SRP value. These are less reactive. Since they are less reactive, they cannot replace H positive from the acid. Okay. Whereas the minus SRP values, they will be replacing. You can do one thing. You can take one nail and put lemon juice on top of it and keep it outside for some time. Tomorrow, when you see that nail, that iron nail, you will see fully it will get corroded. Why it is getting corroded? Because the lemon juice which you have put, the nail has reacted with the lemon juice and it has formed a different type of compound there. Okay. In this way, it is forming from the pure metal, it is forming a metal salt, and thus it is undergoing a corrosion. So in this way, it is displacing the hydrogen from the dilute acid solution. I hope you have understood this one. Yes, let me go back. Yeah, I was here. So here you can see the example. Zinc with H2SO4 will give zinc sulfate with H2. Sodium with HCl gives sodium chloride and hydrogen gas is liberated. But copper with H2SO4 will not react. You can see the arrow mark here. Arrow mark with the slash means it will not react, and copper sulfate and hydrogen will not be formed. Why it is not being formed? Because the copper is having a plus 0.34 volts of electrode potential, whereas zinc is having minus 0.76. So all those metals which are having their SRP less than 0 can displace hydrogen and from the acid and give out hydrogen bubble in the solution. So this reaction is feasible, whereas all those which are having a positive SRP, for example, you have gold, silver, copper, platinum, they will not react with the acids and they will not liberate the hydrogen gas. Next one. So we can actually, by knowing the electrochemical series, we can do the conventional representation of different types of cells. This already we had done. We will revise once again. Daniel cell between zinc and copper. So how do I read? I read that zinc electrode, which is solid, phase difference is dipped in a solution which is having zinc 2 positive ion. This is an aqueous solution. Double vertical line means what, children? It is a salt bridge which is in contact with copper 2 positive ion. That's a salt solution, aqueous. Oblique, again the phase difference, and the copper. So this is a complete setup. So what is your anodic reaction? Remember, Anode undergoes oxidation. Oxidation is loss of electrons. So anodic reaction means there should be loss of electrons. So zinc is being breaking down into Zn2 positive plus 2 electrons. At the cathode, what is happening? Reduction is taking place. Reduction is gain of electron. So Cu2 positive from the solution is accepting the 2 electron and getting converted into copper. When I sum these two, 2 electron gets cancelled. On the left hand side, what will I get? Zn plus Cu2 positive, reversible, Zn2 positive plus Cu. This is my next cell reaction. So all these work we can do by using electrochemical series. Another example, let's take if I have a nickel and tin electrode. Now nickel SRP is minus 0.2550 and my stannous SN tin is minus 0.140. Now I have to think which one will be anode, which one will be cathode. The one which is having the greater negative value will become anode, undergo oxidation. The one which is having the lesser negative value will become cathode, undergo reduction. So who will be my anode? My anode will be my nickel. Who will be my cathode? Cathode will be my stannous. Okay. So in anode, what will happen? Oxidation. Again, basic. Oxidation is loss of electron. Nickel will break down into Ni2 positive plus 2 electron. Cathode, stannous will accept reduction, gain of electron, drag. So Sn2 positive plus 2 electron gives Sn, and the total cell reaction 2 electron cancels. Ni plus Sn2 positive reversible gives Ni2 positive plus Sn. Okay, this is my total cell reaction. And then how do I represent it? Always my anode should be where? My anode should be on the left hand side. My cathode should be on the right hand side. So nickel electrode, phase difference, Ni2 positive, salt solution, double line, salt bridge, Sn2 positive, again aqueous, oblique Sn. So this is my total cell representation. Like this, I can do different cells representation, calculation of their EMF, and then what is the reaction taking place at anode and cathode, everything theoretically by using this electrochemical series. Okay. Now, how to calculate? Calculate the EMF of the cell? We know that the EMF of the cell is E cathode minus E anode. Nowadays, we are having very good instruments, digital instrument by which we can get it directly. But previously, in the olden days, they used to use a bridge like this. Okay, it is also known as a potentiometer. Okay, so in an electrochemical cell, each electrode is placed in contact with the electrolytic solution. The potential which arises at the surface of the separation of the electrode and the electrolytic cell is called as electrode potential. This we have already known. Okay, so when two electrodes are connected, the potential difference arises between the electrodes, and the potential difference between cathode and anode is known as our EMF of this cell. Now, how can I measure a EMF using a potentiometer? In the potentiometer, here you can see there is a uniform wire. AB is my uniform wire. This is having a very high resistance. A storage battery, there is a storage battery which is present here. Can you see here? C is my storage battery. It is connected to the A and B. Okay, it is connected to A and B of the wire through a rheostat. This R is what? My adjustable resistance. This is also known as my rheostat. In first circuit, the cell whose EMF is to be determined is connected to A. Okay, one of the cell, standard cell is there. Another cell whose EMF I have to connect, whose EMF I have to calculate, that is being connected. Okay, and then the galvanometer is my G, and a sliding contact. This S is my sliding contact jockey stick which is there. The second circuit is completed by connecting the standard cell and the galvanometer G. Okay. Now I have key here. Okay, one key is there. Another key is there for my K1 and K2 are used to connect the cell whose EMF is to be determined and the standard cell respectively. So now first I will introduce one key, that is the K1. Okay, and I will take this jockey stick and I'll start moving it around AB. And it is so adjusted that no current flows through the galvanometer. I'll keep seeing the galvanometer pointer. Okay, if it is deflecting means the current is moving. If it is not deflecting means the current is not moving. Okay, there is no current which is flowing through the galvanometer. Let it happen at point D. Let's see that at point D what is happening is there is no current which is moving. Now the EMF of the cell will be exactly equal to the potential difference between A and D. Okay, the EMF will be exactly equal to the potential difference between A and D. Similarly, now what will I do? I'll release this key K1 and I'll introduce another key K2 here. Okay, standard cell and galvanometer, the sliding contact is adjusted. Now again I will adjust the sliding contact such that my galvanometer should not move. Okay, the pointer should not move. Suppose at D1 there is no current which is flowing through the galvanometer. Okay, then the EMF of the standard cell will be exactly equal to the potential difference between A and D dash. So now I got two values. One is AD, okay, that is the potential difference between A and D. Then secondly, I got the potential difference between A and D dash. Okay, so how can I calculate my EMF? There is one formula, that is E of cell by E of standard is equal to the potential difference between AD divided by the potential difference between AD dash. So the E of cell by E standard is equal to what? Length of AD. We have already calculated the length of AD and length of AD dash. When we take these two and then E standard we already know. Okay, E standard value we already know. So E of cell is equal to E standard into length AD by AD dash. Okay, by this formula you can actually calculate the E of cell. Okay, let me again revise it for you. All of you stay together. Okay, so this is a potentiometer. It consists of a uniform wire AB. It is having a high resistance. Okay, there is a storage battery which is C, which is connected at the end of A and B. There is a rheostat, adjustable resistance is there. There is a galvanometer, a key. There are two cells. One is the standard cell. Another one is the cell whose EMF you have to calculate. There are two keys, K1 and K2. For the first time, I will connect the K1. I will take this jockey stick. Okay, I have a jockey stick and I'll adjust it in such a way that there is no current in the galvanometer. Okay, suppose the point is D. Now I will take the distance between A and D. Okay, there is one scale and I will take the distance between A and D. Now what I will write it down in my notebook. Now I'll remove this K1 key. I'll switch on this K2. Okay. Again, I'll do the same procedure. I will take my jockey stick, move along the AB wires such that at one point there won't be any current in the galvanometer. There won't be any deflection. At that point, let's take it as D dash. I have stopped it. Okay. Now here the EMF is equal to the length of AD dash. I will take the value of AD dash and write it down. Okay. Now I'll come to my formula. What is the E cell by E standard? E is what? Electrode potential of the cell upon electrode potential of the standard is equal to potential difference between AD by potential difference between AD dash. Okay. That is equal to length of AD by length of AD dash. You have already written it in your notebook, no? You put those values. E of standard, suppose you have taken standard hydrogen electrode, then the E standard becomes 0.00 volts. Then E of cell can easily be calculated by dividing these two. Okay. In this way, we can calculate the EMF of different cells. Okay. With this, I come to the end of your session. I'm unmuting you people. If you have any doubt, All of you can ask me. Yes, tell me.
Ma'am,
Aishwarya?
how to calculate electropotential of the cell, ma'am? I mean, standard cell.
Standard hydrogen electrode with 1 molar concentration and 25 degrees at 1 atmospheric pressure, that is assumed to be 0.00 volts present. Okay, so that,
Then electric, electric. Okay, carry on, ma'am.
yeah. So we are taking that as 0.00 volt because that's the reference electrode. So any other half cell, when you connect to that, it will be E naught of the cell is equal to E of cathode minus E of anode. One is 0.00, so the other one will be the half cell's value only. Are you getting it?
Yes, ma'am.
See, what is the total EMF of the cell? It is cathode. What is the total EMF of the cell? What's the formula? E of cathode
Cathode
minus
minus
E of
anode.
anode. Okay. Now
Anode.
suppose I take any of, let me go back. Okay, let me go back and show you the electrochemical series. Just 1 minute. Okay. Let me take calcium. Okay, one of my electrode is calcium. And what is the value of calcium? Minus 2.868. Okay. You take your notebook and write it down. Calcium electrode potential is minus 2.868. Now the other one is my standard hydrogen electrode. Standard hydrogen electrode is what? 0.00 volt. Okay. So calcium will act as what? Anode or cathode?
Anode, ma'am.
Yeah. So it will act as anode. So hydrogen will act as what? Cathode. Okay. Now write down E naught of cell is equal to E naught of cell is equal to E naught of cathode minus E naught of anode.
Yes, ma'am.
Okay. So who is your cathode? Hydrogen. Correct? So that is 0.00. Yes? 0.00 is the value of hydrogen. Minus of
Yes, ma'am.
calcium. Calcium is how much? Minus 2.868.
So
So
it will
minus,
become positive. Yes, ma'am.
very good. Positive 2.868. Like this, you get the value of the half cell, calcium. In this manner only, they have taken the values of all these different types of electrodes. By connecting it with the sheet, that is standard hydrogen electrode, that is assumed, because that's the reference electrode, that's assumed as 0.00 volt. All the others will be the half cell value only you will get. Now, did you understand?
Yes, ma'am. Yes.
Yeah.
Thank you, ma'am.
Yes. Any other doubts? Please ask, children. Any other doubts? No? I have unmuted all of you. You can unmute and ask question if you have any doubt. No? Okay. Did you complete your record? Record writing is over. Okay. Then you people must have become very tired, no? Continuous classes.
Yes, ma'am.
Chalo, take rest. I'll see you tomorrow again. Okay. Thank you very much.